So let's begin with what we were doing last time, and then quickly recall what we were doing last time. And so here was the key thing. So we constructed a set of rational numbers, and we saw that this comes out as an equivalence relationship, and it comprises of these creatures. Well, these creatures are classes, equivalence classes, EQ are integers, and Q is not zero. And then we defined addition and multiplication on it, and we shown that basically this guy is a field. So we kind of spent lots of time on seeing that, okay, that how these plus and multiplication are well defined, okay, and how it's a field actually. Okay, so I didn't, I haven't done a complete proof, but I left it to you that, okay, you should do that. The second thing that we did, that not only it's a field, but it's an ordered field. We defined basically it's like an ordered field. Okay. So not only it's a field, but it's an ordered field. Okay. In other words, you can say basically, if you have an order on Q, you can say that some points are in left or are right of some points of Q. So some rational numbers are left of some specific rational number, and some are on the right of some specific rational numbers. Okay. What is the next thing that I would like to do before ending up this discussion on a set of rational numbers? So we had a kind of a new picture. Huh? So we had that, okay, these are kind of rational numbers. Huh? These are kind of rational numbers we have. Okay? But what we would like to see next is that this collection of rational numbers, okay, these classes, is not only rational numbers, but it contains basically Z as a part of it actually. So in other words, in this picture you have some places to which you can say that, okay, that's 0 and that's -1 and that's 1 and so on and so forth. Okay, so somehow if I say that this is my space Q, okay, the set Q, Z is sitting inside this set, okay, and it's sitting as a subfield, and it's sitting as a basically nicely. Now how you can basically prove that within a space you have another space and sitting nicely, and not only sitting nicely, but it's also kind of sitting, it's also kind of inheriting, or maybe having the addition from and multiplication structure, and not only addition and multiplication structure, but also an ordered structure from Q basically. So this space is kind of inheriting. So in other words, when we constructed Q, we haven't lost Z. Z is still there. That's a key thing that I would like to emphasize on. And in order to do so, whenever we have to prove, so technically we call it that Z is embedded. So that's a symbol that we are going to use, that Z is embedded in Q. Okay? So that's a symbol. So how are you going to read it? You read it that Z is embedded in Q. Okay. So in other words, within Q, there is a photocopy or maybe isomorphic copy. Okay, so like a photocopy of Z sitting inside Q actually. Okay, so how are you gonna recognize it? So whenever you have to show that something is embedded in Q, you have to show two things. Number one, that you have a 1-1 map, not a bijection. Why? Because if you have a bijection, this means that Z and Q are, equivalent actually somehow, which is not the case. Obviously, there are rational numbers which are obviously do not correspond to any number in Z actually. Okay. So what we have to do is to prove to define a map from Z to Q. Okay. And that map is 1-1. In other words, when you are saying that okay, you have a map from Z to Q and which is 1-1, but actually you are showing that Q contains at least this much number of points. Okay, so Q contains at least this much number of points. Okay, so that's one of them. And secondly, the word embedding also means that okay, whatever structure this Z which is sitting silently within Q also preserves that structure. Okay? And what is the structure of Q? So you have addition, multiplication and
order.
so in other words, this photocopy of Z is sitting in Q and it's playing nicely with addition, multiplication and order. Okay? So that's what we're going to basically do. So that's a kind of intuition and let's do it precisely. So whenever we have to, represent such kind of embeddings and especially canonical representative embeddings, we use this symbol pi basically. So it's like a pi is sometimes used as projections, as embedding and many different ways. So I'm defining a map pi which is a map from Z to Q. Okay? We need to keep one thing in head that Z contains integers while Q contains classes. Contains classes which are rational numbers actually.
Yes, sir.
Okay? So if I like to define a map pi onto n where n is some integer, what do you think that what should I have on other side? In other words, this n is sitting as a clause in Q, but what is that clause? What do you think? What's your guess actually?
N comma 1 or n over 1.
So it should be
N over 1
n
or
comma 1
n comma
or n over
1.
1. Okay. Right. Alright, so it should be n over
1.
because if I have an n here, then there is a corresponding clause which is n over 1 here, which behaves like n actually. Okay. So what we have to show next is that this map is 1-1. Do you think that this map is going to be 1-1? Check yourself. Check yourself that this map is 1-1. Okay? It's like an injection, huh? So it looks trivial, but really you need to show it actually. Okay? In other words, if I have 2n and m from Z and their images are equivalent, equal, then these numbers are going to be equal. That's what we have to prove actually. Okay. So in other words, that is what you're going to have n over 1 equal to m over. So in other words, if two classes are equal, okay, then you have to show that these representative are going to be equal. Okay. So that's what you have to think for yourself. That how you gonna. And if obviously these two classes are equal, then let me read out that
Sir,
if the representatives are equal.
n comma 1 is related to m comma 1, which implies n is equal to m.
Exactly. So from where you can drive basically equality of finite. Okay? Now what is meaning of, as I said, that Z, the copy of Z which is sitting within Q is playing nicely, with respect to addition and multiplication. So you might have seen something like similar actually in linear algebra course. So there you have what you call the homomorphisms, or what you call the linear transformations. What was the linear transformation? The linear transformation was kind of a map between vector spaces, okay, which plays nicely with addition and scalar multiplication. In other words, that you add two vectors and transform is same as that you first transform them and then add them. Okay?
Yes.
And similarly, so it's like playing nicely with addition. So how about here actually? What do you think? What should be done? So in other words, so that's the first property that we need to verify, and the second property that we need to verify is going to be that if you have, so if you take two integers, say n and m, and you add them and consider the class of it, it should be same as
Pi of
m plus. Okay. So in other words, class corresponding to this sum should be same as the sum of two classes. Okay. So obviously you can't put plus here because here, since these two are classes, you need to put this plus. Yeah? Okay. So the plus that we have defined. And how about the and in order to do so, in other words, how are you going to show that? So what is going to be the n plus m? Pi of n plus m. So it's going to be n plus m over 1. So you need to show that the class n plus m over 1 is equal to the class n over 1 plus m over 1. So that's what you have to show mainly. Okay? Just show that. Did it?
सर आपने मतलब कहा सेकंड प्रॉपर्टी वो नहीं चाहिए जो एम्बेडेड मतलब जो बड़ा वाला सेट है उसमें जो प्रॉपर्टी वो छोटे वाले में होनी चाहिए स्ट्रक्चर सही है सर फिर ये मतलब प्रॉपर्टी को कैसे शो कर रहे हैं सेकंड नहीं यहाँ पे नहीं पहला वाला आगे समझिए सेकंड उस चीज को कैसे वेरीफाई करें
just think about it. We are saying that if you take two elements, okay, from here, okay, and so it's like we are taking two elements from Z, okay, and we are considering then the class corresponding to their sum. Okay, so the class corresponding to sum should be same as that you have
two classes and
classes, so it's like a sum of the classes. So if you do that and if you have that property, in other words, you're gonna say that yes, Z basically, the copy of Z which is sitting inside Q is really behaving like basically in the sense of addition like Q actually. Okay? So in other words, you add two numbers and then consider the class, or you sum two classes and then consider basically what you have there. You consider two classes and then sum them basically. So it's like setting up a sequence. Okay. So how about what is your guess about how are you going to show that? Will you be happy to do that? Because this thing is what actually? So we have definition for this. So what is this? So this is n plus m
comma 1
upon 1 times 1. So which is same as m plus m over 1. So we already proven it actually. We've shown that this is same as this class actually. Okay. So we need to show that. We just shown it.
So
There's going to be something trivial.
like taking right hand side, converting it into.
Yes. So it's like take it from side and transform it. Try to transform into other. Okay. How about the third part? What do you think? What do you need to do?
Product.
Does it? Not scalar product, but product here actually. In other words, if I have two integers and I multiply them and then I transform them, okay, is it same as that you take the product of the classes? Okay, that's what we have to verify. So interestingly, just like it's going to show that basically Z is kind of inheriting this, copy of Z is inheriting, the addition and multiplication structure from Q. Okay? That's what we have to verify. And what will be the last part? There you go. Are you writing this? Okay? Are you done with it already? Okay. So, what will be the next thing? And the last thing, and a crucial thing actually, that Z is not only inheriting addition and multiplication from Q, but it's also inheriting order basically. It's also respecting order. What do you mean by that? In other words, if you have two numbers and one of them is smaller than other, and you transform them, in other words, you take the same two number into Q, or in other words, the copy of Z in Q, their order is going to still preserve basically. So in other words, the class n over 1 should be smaller than basically what n over 1. Okay. So in other words, the second thing that you have to show, that it's also respecting the order. What do you mean by that? That if n is smaller than m, okay, then pi of n is smaller than pi of m. Okay? So the pi of n is pi of n is smaller than pi of m. Okay? How are you going to show that? So that's my assumption, and that's what I have to prove. Now what is pi of n? That's n over 1. And what's pi of m? That's m over 1. Okay? And what is the meaning of order? In other words, what is the meaning of order in Q? So what is the meaning of less than? Huh? What is the key thing there basically?
Smaller or greater?
Huh?
m
Smaller or
minus 1 is less
So in other words, how you can know within rational numbers, set of rational numbers, that one rational number is smaller than other.
because the difference
Is positive. So in other words, you just need to check that if the difference of m over 1 as a class and n over m as a class is positive, and we defined actually that what is the meaning of difference, or what is the meaning of something being positive actually. Okay. So in other words, if I take m over 1 and add minus n over 1 to it, okay, isn't that the same thing that you are subtracting? Minus n over 1. So it should be positive actually. It should be greater than 0. And how you can say that basically this is positive? How are you going to say that? So you just apply this definition, and what will be that definition? M minus n over 1. Okay. And if this a rational number, a positive rational
Yes,
number?
sir.
Yes, sir.
Because hypothesis or given.
No. We also defined that when a p over q is positive, how are you going to know that a rational number p over q is positive? So I need to do that. You take the denominator and numerator and multiply them. Okay. It is positive because if you take m minus n and multiply it with one denominator, it's equal to m minus 1, which is greater than 0 because n is smaller than m. Okay? So, that's it. Okay? Is it making sense? That what you showed actually, that if n is smaller than m, then the corresponding class in Q, which is corresponding to m corresponding class to m, which is corresponding to m, which is pi of m, should preserve the basically same. So it's kind of order is preserved actually. So it plays nicely with Q. Okay. You happy with this? Alright. So let's move ahead. So we create a beautiful creature. Okay, just like as we have this creature with us, Q, which comprises of classes P over Q. Okay, with this description. Now, I mean, if we want to have a picture, what would be our picture? So after proving this result, what we have picture? The picture is going to be like that. Okay? So we have loads of rational numbers. Okay? So not only we have loads of rational numbers, but we have also integers sitting between them. So maybe, maybe 0 is here, and -1 is here, and 1 is here, and so on and so forth. So this line contains 0 and 1. And since we have order, so we can put, we can say that this rational number, is on the left of -1 because this is smaller than -1 actually. So we can have this picture. Okay. Now here is a very interesting point to observe. You might have seen this result before, but we can prove it easily. That between any two rational numbers, you can always find a rational number. Get it? Between any two rational numbers, you can always find. In other words, if I take these two rational numbers, I can find a rational number in the middle, and I can find a rational number in the middle, and I can find a rational number in the middle. In other words, I can find as much as rational numbers in between. Okay? So what do you think that is this picture, if after putting say loads of rational numbers in between, is this part is going to be kind of complete actually? In other words, can we have no gaps in between?
Can,
Huh?
what about irrational? I think they are the kids.
So we need to think, what is the rational? We haven't defined it.
We can't discuss it.
So first we need to demonstrate that there are things which cannot lie on any of the rational number basically. So in other words, hence there are things which are kind of gaps in between actually. So which you can't, kind of indicate on rational numbers. So there are going to be more than that. And what is the easiest way to show that? What do you think? Do you know any such thing? Any such thing? Which you can't put it on, rational line, this line. Any such thing?
Pi.
Huh?
Pi.
What's pi?
We don't know.
Sir, algebraic
Error.
number होते हैं और वो नंबर जिसके सॉल्यूशन नहीं होते वो वाले नंबर्स
वो यहाँ नहीं आएंगे.
They are part of irrationals.
Huh?
They are part of irrationals. We haven't discussed them.
We haven't discussed.
We don't know.
So can we talk about such numbers without giving a reference of something like irrational numbers? We don't know. We haven't defined it yet. Okay, you can define it something which is not rational. But the question is that are there numbers which are rational? Maybe there are only rational numbers. But how you can demonstrate it basically that yes, there are numbers which are not rational.
if p and q are not integers, yeah, p upon q
Are not integers. But what is the meaning of
being not integers.
not integer?
If they are not integer,
Then they are rationals.
They are rationals. Okay, you have rationals. But you can have rationals divided by rationals. So maybe you can get
Another rational.
another rational action.
So you are there still.
Okay, the question is still there. Okay. So in other words, we can say that this Q is good. Why? Because this can answer such kind of questions now. We can answer such kind of. So which is the number which satisfies this equation? So we know answers of such questions. But do we know the answers of other questions?
X square is equals to 2.
So do we have? So it's not good enough. So the Q is not good enough. Why? Because x squared is 2. But how do you know that you don't have the solution of x squared equal to 2? So maybe there is a rational solution. We don't know that. But we can show that actually. We can prove actually
there is no
there is no
Rational solution.
there is no
rational.
x in Q such that
X
x square is Q. How are you going to show that?
Contradiction.
So we have done it so many times. Okay? We can say that suppose there is, okay? Suppose contrary that there is P over Q, but then you can show that okay there is going to be a contradiction and trouble. I'm not getting into that proof which is well known, so I'm not getting into it. Okay? So there are equations which maybe this Q can't handle actually. Okay? So, but still it's not giving a kind of an explicit view that why there are gaps in this line. Okay, so let me give you an example. What if I take a right angle triangle with length 1 and 1? Then the length of the hypotenuse is going to be something which you can't put on a real line, okay, which is not rational actually. And so it is, okay, it is something that we today call it the square root of 2, but we don't know that what is the square root of 2. We need to define it, we need to justify. So in other words, why I am saying that though there are lots of irrational numbers between irrational numbers, but still there are going to be holes. So in other words, if I have to show this length, so it's going to start from 0, but it's going to stop somewhere, okay, which is not corresponding to basically any of rational numbers. It's like going to be what, 1 point something, which is not corresponding to any of rational numbers. And hence we say that in our picture is not complete, there are gaps in it. There are gaps in it. So what is the next thing that we want to do is to fill the gaps. Okay? And
Sir, is it necessary to fill them?
Yes, because if there are questions, we must strive for answers again. So in other words, here you have something very challenging. Here is a algebraic equation with rational coefficients. It's telling you, catch me if you can. The solution of it is saying to you that catch me if you can. So if it is saying we should accept the challenge. In it. Okay? Is it making sense? Good. So let's try to fill the gaps. And for filling the gap, what we are essentially going to do, we're going to begin with defining some of the terminology, and after defining that terminology, I'll state a kind of a key theorem for this whole discussion. Okay, so consider this interesting set. Consider this set. So I have a set A, okay, which comprises of those numbers of Q such that x square is less than 2. Okay. So how many of points from this line this set is going to contain? Just 0? No. How about if I take -1 square?
-1 to
-1 square. So it's going to still satisfy that. Okay, so how many of rationals? So it's not going to contain whole rational line, obviously. Okay. So it can contain things from something, from one gap to another gap actually. So it's like it's going to contain things from one gap to another gap. So it's going to contain all rationals between two gaps. Okay? It's something very interesting. But can I say that there is a rational number, okay, which is going to be bigger than every rational number here in this cell? Can you tell me a rational number which is going to be bigger than this rational number? Or all rational numbers which are here actually?
Yes.
For example,
3, 4, 2, 3, 4.
we begin with 2. Okay. So is 2 is upper bound for that?
Yes.
Basically bound for that. So in other words,
define
so
bound.
every element, so we need to define the bounds. So it's like, yes, there are numbers which are bigger than all of the rational numbers which are sitting here. And you can even find some rational numbers, not some but lots of rational numbers, which are smaller than each of the rational number here. making this. Okay. So in other words, we can have something which is the notion of bound. So the first thing that I would like to define is upper bound for a set. Okay? Upper bound for a set. So what do you think, what should be the definition of an upper bound? So I'll say that let A